So the diagram A below shows a graph of a displacement y against a distance x for a progressive wave at a certain time. At the time, let's say this is t, 0.4 seconds later, the profile of the wave is shown in the diagram B. So we can extract some information from the graph. The first thing is the wavelength. You notice that this is a complete cycle for a wave. So from 0 to this point 0.02 meter is given by if wavelength. So lambda equal 0.02 meter. And now after the time t 0.4 second later, let's say we take this for a reference point 0, start from 0, then end out with the 0.10. So this is the distance traveled, so equals to 0.10 meter. And you can take other reference point if you know what you are doing. For example, you can take 0.02 meters from start from here and end out with this 0.12 meter. So you can write like this: 0.12 minus 0.02. You will still get the same answer, 0.10 meter. As long as you know what you are doing, it is okay to use any point for reference. And now we want to find out the frequency. So we can find out the velocity first. V equal x per t, so equals 0.10 per time, 0.4 second. So the answer is 0.25 meter per second. And now we can find out the frequency by using V equals F lambda. So 0.25 equals F. Lambda is 0.02. Our frequency is 0.25 divided by 0.02. We get 12.5 Hertz. So the correct answer is D. The graph below shows the variation of acceleration A with the displacement x of a particle performing a simple harmonic motion. So the question 1, the frequency. This one we can directly apply the formula for simple harmonic motion. A equals minus omega square x. We take the acceleration A to be this 0.6, so we have 0.6 equals minus omega square. At this acceleration, it corresponds to the minus 0.02. So this is x minus 0.02. We solve for the omega. We will get the square root of 13 radius per second. And omega is also equal to 2 pi f. Now this is square root of 13 equals 2 pi. We find out our f. So you will get a 0.87 Hertz. So the answer is A. A particle performs an oscillation without damping. Which of the following quantities is not constant for the oscillation? We first look at the A here. The force is given by ma, and in the oscillation case, the acceleration is equals to minus omega square x. Now we substitute this acceleration inside the force formula, so we will get minus m omega square x, and this x is a displacement. So we can see that the force is depends on this displacement here. So the force is not constant. So the answer is A. But we have to take a look for the B, C, and D. This can build out our understanding. We have to explain why these B, C, and D are wrong. Of course, you will not get marked for this, but this can build out your understanding about what actually happened. Now we take a look at the B. This is the amplitude. If we draw a graph for the x displacement against the time t, this is a graph we will show, and the amplitude is defined by this maximum displacement from the 0 point. So in this case, we will get here is the maximum displacement. So this is A, and after time t, this A is still at the same. So the amplitude are constant because this is without damping. This is a keyword. And so B are wrong. Now take a look at the C. Total energy. The formula for the total energy is given by T total equals 1 over 2 m omega square a square. And since the amplitude is constant and omega is constant, the mass is also constant, so the total energy is also constant. So it is not the answer we want. And just in case you are wonder how we derive this total energy, we can one approach is start from the kinetic energy, which 1 over 2 mv squared. And in the case where the velocity is maximum, so max, we can get our total energy. Now we apply the V equals omega square root a square minus x squared. Now when V is maximum, the x is equal to 0, so we will get omega a. And then here we substitute this V max inside here. Yeah, and then we can get our total energy. So this is not our answer. Now how about D? D is angular frequency. The angular frequency is given by omega. This is constant. It does not change from time to time. So D is also not our answer. So the correct answer is A. When sound wave will propagate in A and two particles which 0.2 meter apart vibrate antiphase, if the speed of the sound in A is p20, let's mark this to be V, and the question wants us to find out the frequency. So now we have an antiphase here. That means the two particles are 180 degrees for the phase difference. And now we have to find out the lambda first. We know that lambda corresponds to the 360 degrees, which is one complete cycle. And here we have 0.2 meter are corresponding to the 180 degrees. So we take this as a ratio. We will get lambda equals to 0.4 meter. And now we just use the formula V equals F lambda. Now V is 320 F, and wavelength is 0.4. So we get a frequency is equal to 800 Hertz. So the answer is C. The standing wave from the spring can be produced by vibrating one end of the tune string at a certain frequency with the other's end fixed. So the standing wave can be also produced in a closed pipe by putting a vibrating turn flux near the open end. Which of the following is true of the standing wave on the spring and the standing wave in the pipe? The A, both standing wave vibrate with the speed of sound in A. This is incorrect. Clearly, for the string case, they are not going to be vibrate with the speed of the A in the sound. It depends how we vibrate it. So the A is incorrect. And the B, the sound of the bow standing wave cannot be here because the standing wave do not propagate. This is incorrect. Clearly, if you're vibrating a turning fork near the open ends, you can clearly hear the effect. Now C, the standing wave from the spring have a knot, while the standing wave in the pipe does not have knot. This is incorrect. For all the standing wave, there will be a anti-knot and also knot. So D, the standing wave on the spring are transfer wave, while the standing wave in the pipe are longitudinal wave. And the D is correct. This is because for the spring, we know that this is, let's say this is a spring, and we vibrate it. And now we can see the direction of this displacement is going to positive y direction, but the wave travel back and forward here to produce the standing wave is 90 degrees to the displacement of the particle which inside the spring. So this is a transfer wave by definition, and the standing wave in the pipe is the sound wave. As you know, the sound wave is a longitudinal wave because the vibration of the A particle is parallel to the direction of the wave propagation. So the D is the correct answer. The diagram below shows the variation of the force with the separation R between two atoms. The shaded area represent. So first thing we have a force and we have separation R. And we know that the work done is equal to the energy required, U equal to integrate of the force dot dr, which give us this shadowed area. So the graph here, the diagram here is given us the energy to break the bond between the two atoms. So the answer is B. Now we take a look at the answer A, C, and D. The A is incorrect. It states that this is the energy required to ionize both atoms, and the ionize means that the atom lose the n electron. They have nothing to do with this separation R between two atoms. So this is the A is incorrect concept. Now the C, the kinetic of the two atoms at the equilibrium separation. This is also incorrect. It does not mention anything about the velocity or motion, so the kinetic energy does not involve in this case. So C is incorrect. The last one, D, the energy to change the bond in the solid state to the bond in the liquid state. This is totally does not mention, does not have a relation shape for this diagram here. So the correct answer is B. A wire is stretched without exceeding a proportional limit. The following data is obtained. So we have first in the force, and we have a cross-sectional area. We have extension x, and we have the original length of the wire. Which of the following statement is not true? You want to find out the not true one. First, the A, the string, is defined as x per L. So we get a 10 to the minus 3. So there is no unit, and this is true, but it is not our answer. We want to find out the one is not true. The second is the stress. Stress is force per area is equal to 100 divided by 10 to the negative 6. So we get 10 to the power of 8 Newton per meter square. So this is also not our answer. And the force constant, this one we apply the Hooke's law, F equal minus kx, and we substitute the F inside, also the extension, okay. So we get a 5, and then 10 to the power of 4 Newton per meter. So this is also not our answer. And the last one, the energy store. The energy store is given by 1 over 2 kx squared, and now we have a k here. The extension, So we get a 0.100, and so the energy stored in the wire is given by this value 0.100 joule. This is not not true. So this is our answer. Our answer is D. And by the way, for this formula for the energy store is also can be written as 1 over 2 f x. You will get the same answer because the x is just minus kx. If substitute this inside, you will get the formula I use. But both will give you a correct answer. Which of the following influence the degree of freedom of a gas molecule? A. The number of atoms per molecule and the temperature of a gas. So the A is correct. This the number of atom per molecule will define whether the gas is the monoatomic, diatomic, or polyatomic. So which have a different degree of freedom. And the second thing is the temperature. In general, the temperature increases, the degree of freedom is also increases. So this is a two factor will affect the degree of freedom. So the correct answer is A. And the B stat here the mass of the gas. This is incorrect. The mass of the gas does not influence the degree of freedom, and the pressure also does not effect on this degree of freedom. So here we can see the rest is incorrect. The correct answer is A. The RMS speed of the molecules of a certain gas is C. When the volume and the pressure of the gas are double, the RMS speed of the gas molecule is. So now we first have to write down the formula. We let the temperature T with the RMS speed C. So this is a formula. And we can see that this T is proportional to C squared. And now we apply this PV equals to nRT. Now let's say we have temperature T2 when the volume and the pressure is double. So we have 2P and 2V equals to nRT2. And if you divide this, let's say this is equation 2 or formula 2, we divide this equation 2 with equation 1. You will get 4 equals T2 per T, and this PV can be cancelled out, P and V, and NR can be cancelled out, and so this is the result. Now we apply this relationship here. We can write this T2 per T equals to C2 squared and C squared. Now this ratio T2 per T is equal to 4, or we just from here we write this equal to 4, and we solve for C2. You will get a square root of 4C squared equals to 2C. So the answer is D. The graph below shows the variation of a pressure P with the volume V of an ideal gas undergoes a cyclic process. The point P, Q, and R represent the three states of the gas. Which state of the gas are the coolest and the hottest? So we use PV equals nRT, the ideal gas law, and T is equal to PV per and R. So let's say we calculate the temperature at the Q state first. We have four pressure here. This is volume is 1. So this is 400 per n-hour. And now we calculate the temperature as P, and this is 1, so 10 to the power of 5 and 10 to the negative 3 and R. So this one we will get 100 per nr. And now calculate for R. R we have so 500. So since this n and r is a constant, so we can directly compare the value above here. So we have 500. This is the highest hottest. So this is R. Now we take a look at the coolest. Coolest should be this 100 here. So this P is coolest. So the correct answer is B.